Doing well. Excited to be here. I'd like to thank Russell for his organization of this event. This is a very exciting time. I came to Goddard Space Flight Center at about 1996, and pretty soon I got involved with the nano-satellite technology development effort over there, working with automation and autonomy for that specific project. And we were also very interested in getting commodity processors on board spacecraft because the commodity processors seem to have good radiation tolerance properties, and they had much more computing bandwidth for the buck than the rad hard parts we could get our hands on. We spent years trying to get our projects into space, and one of the exciting things that I'm learning from this conference is just how far we have come in making space available. The cube is really helping us to accelerate our possibilities. And as one of my favorite technologists says, Paul Graham, he says that one of the things you want to do is to accelerate hindsight. And it's great to see the cube technologies come in and start to make that possible. I'd like to also thank Pamela Clark. We're involved with the Frontier Design Project that was supported by DARPA, and we'll come back to that. But one of the main things, also Dr. Steve Curtis, who helped lead us in some of the efforts with some of that nano-satellite, nano-spacecraft technology, who helped us figure out how you'd actually control these large groups of interacting spacecraft, and that work led to a number of patented technologies. My main goal here today is to generate discussion. This is just the starting point here. If you want to have a network of assets on the moon which are producing data that's important to you and bringing that back, then there's a lot of work to do, a lot of things that we're going to have to do together. It's like they say, it takes a village. Well, we need to build that village. We need to build that community so that we can identify where there are gaps with where we need to go with these technologies, and how we can actually influence existing capabilities, people who are actually putting things into the moon. How do we influence them so that we can take part of that? I'm new to the cube, to the lunar cube effort and the cube technology effort, and I just listening to Russell the other day talk about all the moon missions that we have coming up in just the next few years. How do we get a footprint in those missions so that we can share some of those resources? One of the things that I'd like to mention or talk about is that the cube is a disruptive technology. We're going to be in niches for some time until we become capable enough to supplant the incumbent technologies. So we're going to have to be the second sister. We're going to have to play. We're going to have to deal with the leftovers, and we're going to have to work within other people's margin. That means that we're going to have to be good players. We're going to have to play well with others. So one of the takeaways I want to talk about, I want you to come away with this talk, is that we need to build a community. We need to share that knowledge. Who is putting the opportunities and resources together that we can actually help use so that we can put our little piece in and get the data that we want to get out. Also, because we are talking about space systems, we need to support multidisciplinary activities, because for space exploration, data is important. It's a system driver. Everything is linked. If you increase the bandwidth in one way, for one thing, it affects power, it affects mass. So we need to be able to put together a complete solution and make arguments for those complete solutions. One of the things that we did at Goddard around the turn of the century dealt with the nano spacecraft effort was that we put together a design reference mission for the Revolutionary Aerospace Systems Concepts effort, the Prospecting Asteroid mission. And this is a 2035 target mission, a line in the sand, something that you can take a look at, assert what you need, and then propagate things back. And it's very similar to what Abraham just did on the moon as well. We had about 1,000 nanospacecraft working together to survey about 1,000 asteroids, in about a 5 to 6 year period. And some of the things that we came away from that study exercise was that, well, you're going to be focusing on nanospacecraft, delta V to move around, but you're using solar sails. In order to get the best bang for the buck or the bang for the kilogram, these individual spacecraft were specialized. If you wanted to get a particular kind of data from an asteroid, X-ray fluorescence spectrometry, magnetometry, you would build a spacecraft that would be focused on that particular goal and put that sensor into the right place. And then what would happen is that to build a complete solution that had the appropriate communications, that had the appropriate computer bandwidth, it would depend on teams. So we'd start with 1,000 spacecraft, work with teams of about 20 individual spacecraft, and then you would use the inherent redundancy of that large number of group to reshuffle around the teams for graceful degradation as the systems would fail over time. In order to do this, you needed to have a very autonomous networks of spacecraft. It's essentially autonomy at every level. If you're going to be operating a system with about even 100 spacecraft, you need to make sure that that system is no more costly to operate than, say, a single spacecraft system is today. And you have to have that inherent kind of scalability. And that's something that's going to come up again and again, particularly when you start talking about networks of lunar cubes on the moon. One of the other things that we talked about, using existing infrastructure and assets, moving data around for this asteroid mission concepts, we actually had to come up with specialized spacecraft for long and short range communication, and we're actually going to carry the data to a point where we could reach an existing asset. And it was pretty easy to say that, well, we have a very high bandwidth pipe opening up at Mars, and so we'd drop down from the asteroid belt, send a few messengers down to Mars to transfer that data back. Again, multidisciplinary. Mission ConOps is tightly coupled to the info system needs, so you always have to come back to coming to a complete system solution. An important thing is that when you're dealing with scientists, the data is the king. So there's a prominent Earth scientist over at Goddard, and one of the things that he observed was that, well, the supercomputers, that technical capability comes and goes, but the data is forever. The scientists, the explorer, they want that data to come back. So one of the things that this is interested in, when you talk about deep space information systems, that covers end to end. So we're only going to get about 5 millimeters down in terms of technical depth for this presentation. But there's an interesting model of development that we can work with. We don't have to invent the process here, because we have seen some extraordinary things going on over the past few decades, driven by technical progress. For example, if you went back to the late 60s and early 70s and looked at what was available for computers, the IBM mainframe, they had memory management, they had memory protection, they had multitasking, they had virtualization, they had all of those things. And if you had the foresight to take a look at Intel and look at what the roadmap has been well, now you look back in time, take a look at what the roadmap for Intel has been. It's essentially been taking those features and putting them into the microprocessor. So over time, that microprocessor has added more and more features. Now you have all of those mainframe capabilities in the Intel server chips. We can do the same thing with the Cube technologies and the spacecraft. Now that we can get things into space and that we can get that space heritage. So an interesting point there is that who's going to democratize the information systems, the operating systems at all, for our cube, for our networks of cubes that we're going to have in near Earth and deep space. That's one of the reasons why we need to build this community, this special interest group that Abraham talked about. One of the things that we did at Goddard is that we did a lot of work in trying to figure out how to get commercial off the shelf more rapidly into space. I can't say that we were very successful in that, but now with Cube, that is becoming much more easier. It's great to see that acceleration. Cube is not growing into a vacuum. There's a deep experience that already exists in space systems. A lot of that is represented by folks in this room as well. We need to buy into that. Take what exists, play that IBM to Intel game, what are the capabilities that you already need for those space systems, and then start to bring them into Cube. Another thing that a community can do is that as a community, we can start to talk about priorities. What can we work on? What can we apply our resources to? What can we seek resources to in order to move things from the larger group, from the more conventional space, and put that into the smaller form factors? And again, the conventional space guys are interested in this because they have a problem. It's large unit costs are driving an interest in tech advance, and that's something that we can help with. An interesting thing is that when you're dealing with national asset style spacecraft that have to work, they put in a lot of margin. They're somewhat over-engineered. That's something we can take advantage of. We can work and actually live off of some of that margin. So that's something to think about when we're putting together our complete solutions. So Cube evolutions, use analogs from conventional space, over time pull more features in. Another point is that, you know, there's this saying is that when county water gets out to a new place, that's when you start to see the land development and the houses go in. We have the same thing going on here. What counts as near Earth versus what counts as deep space will change over time. I could argue that Mars, yes, it's deep space, but there's a really nice communication systems there that you can buy into. And that's something that we need to work on. As a player, people interested in Cube technologies can help those folks. They can be part of the complete solution for the more conventional space capabilities for when they're trying to make their pitches and get support too. So, and again, multi-spacecraft operations must be no more costly than single ones. An interesting point that is both a strength and a weakness is that Cube is not primary or critical. It's going to be a niche player for some time. That means the Cube has to be resilient. It has to be able to wait for resources, and if something more important comes along that calls those resources back, the Cube has to be able to give them up and still be able to live. So that points to a kind of autonomy and adaptability. Cube, you have to fit into it. So you have to efficiently use limited resources. That means that you also have a lower cost to buy into the game as well. And again, because you're going to be niche until you take over, you have to make effective use of the poor real estate that you may get. Space systems development is difficult. It's multidisciplinary. There's a lot of things that go on. You change one little thing over here, and it changes the entire system. You have a complex trade space to work with. For information systems, you have the operational elements stretching from ground out to space. It's very multidisciplinary, and for Cube and for getting to some of the advanced things that you're interested in, you're going to have to be creative. So that means that there's an entire set of needs that you need to work with. Flight software, the tools. We'll be getting into some very interesting developments later on in the discussions that we're having today. Mission modeling, simulation, and testing. We need to make sure that we can argue that we have complete solutions, and we also need to identify tool chains and gaps. And how do we enable a large group, that democratization that Russell talked about? How do we enable people to put together arguments based on Cube, or solutions based on Cube technologies? DARPA is also interested, or has been interested, and the Air Force has been interested in this for some time, because they're trying to break out of those big monolithic spacecraft, those big national asset things. They're trying to make things a bit more adaptable and a bit more defensible as well. Pamela, I, and a group of others were involved with a system trade analysis tool set called Frontier, and the idea for that was to build a collaborative model-based engineering environment where you could bring people who had needs and people who had solutions, bring them together on the web and build models that would essentially be that systems engineering solution that we were talking about. It was an exercise in market building, so where you could have a large group of people publish their solutions and their requirements on the web, and our system would help make those into reasonable, viable systems, and perform that level of the systems trade analysis. The F6 system itself that DARPA was trying to put together, it's the Future Fast, Flexible, Fractionated, Free-Flying Spacecraft effort. There are ideas. Take a look at the last two items there. They wanted to come up with an open source development kit for spacecraft behavior and communications. Okay, and that's something that I think rings really true with the Cube community as well. We would like to have that sort of development kit to help us put together our own solutions. And the other idea is that there's this idea of a backplane in space. If you think about the old ISA bus and all the standards that it was built on, that was really the secret sauce that went into the PC. You could connect anything to it and make it into something that you wanted. So the idea here with the backplane in space is that you put up your system, you put up your specialized spacecraft, and it works as part of the team. It gets communication, it gets other things that it needs from being part of that constellation of spacecraft. So, and I think that's kind of one of the places where you want to get that sort of backplane in space. Eventually, when you start talking about having 100 different cube-based landers and orbiters in the lunar scenario. Frontier itself was a distributed web-based collaborative engineering, domain-specialized user interfaces. It was really a way so that people from different domains could get together on a trade space study. There was also one of the interesting things that we were putting together with that. If you're putting together one of these multidisciplinary models, it's a good idea to have something that would check that to see that the model actually made sense, that it actually had that it could line up with something that could actually fly. And so we had some intelligent model checking and scenario analysis in there so that you could actually make sure that it made sense. If you're familiar from the architectural domain, ONUMA has a building information management storm where you have crowdsourcing, where you have people from all over the world coming together to provide essentially trade space and systems analyses for architecting and designing buildings and spaces. So that's one of the things that we were working towards for that one, another community idea. So the challenges of the monolithic national asset class missions are only going to grow as our needs grow. Cube enables point role optimization, and then you have teams of them working together. In order to do that, they're going to have to be resilient. You're going to have to build some autonomy in there so that they can keep track of themselves and take care of themselves until they can get back around and talk to you again. Leverage what exists in conventional and aim for a complete solution. But we need to help each other to make that story, put that story and vision together. So to take away, back to that first slide again, we need to build a community. We need to build a marketplace so that we can come together and provide each other the information that we need so that we can come up with compelling solutions. We're going to be a niche player for some time until the disruptive technology can take over from the incumbents. So I really do think that Cube is onto something. We're accelerating hindsight, and if we work together, if we bring these multidisciplinary efforts together, then we can make that compelling argument. And so that concludes my talk about enabling information systems. And then now what we're going to do is that we're going to go on and talk about some very interesting dimensions in core software and communications for Cube. So I can be happy to take on any questions that we have during this remaining time.